Good afternoon, all. So welcome to formal software verification track. So our first speaker will be Roderick Chapman. He's from Protein Code Limited. He's an independent consultant software engineer. And then he will brief on the topic development and formal verification of secure updates for embedded systems. Chapman is an independent consultant software engineer and specialties in the development of safety and security critical systems. From requirements engineering through architectural design and implementation to verification, audit, and assessment. Yeah, welcome, Roderick Chapman.
Okay, thanks very much for that kind introduction. I realise I have to speak into this microphone. It's a wired microphone, but I do tend to wander around. So if I get to about here, please all start screaming at me, and I'll try and come back this way before the laptop follows me across the room. So this is a sort of a report from a real project. I'm not just going to tell you about how this works in theory or on paper. We actually implemented this for a UK defence company, and I led the team that implemented this stuff in software. So people call this over-the-air update or remote update. You know, a lot of people just call it patching. This idea that you can marvelously update your software to a million things that you've sent into the field, and you can marvelously just send software updates out there and it all happens. Everybody seems to want to do this, but what I want to give you a brief flavour is to give you a brief flavour of how it works under the hood, or how it's supposed to work, and actually some of the more difficult problems with doing it. Because once you've built this infrastructure, you'll discover that operating it is not as trivial as you might imagine. So the problem is, how do you push software or firmware, images, or just data? Maybe it's a big bunch of data, some tables or something. You just want to get binary stuff out there in the field to your products which you've sold. Might be a couple of hundred products. It might be a couple of million products if you're a car manufacturer and you want to get updates to them. And those systems are remote. They may be out there anywhere in the world. They may or may not have regular access to a network, a sort of internet-style network, or not. So the things are remote. They may be difficult to get at. They may be systems which are intrinsically tamper-proof or dangerous. And the components themselves may actually be very critical in that they may be marked. They might be marked official sensitive or secret or something, or they might just be the intellectual property of your organization. They may have commercial value to you, and you don't want somebody observing or snooping on your updates as they fly out into the world. So you wish to protect your property. So how do you do this? The old way to do it was to get a 3¼ inch, for those of you that remember 3¼ inch floppy disks. You got a floppy disk with your software on it, you stuck it in a suitcase, you locked the suitcase, you padlocked it to your employee's wrist, and you sent them on a plane off to Timbuktu or somewhere, and you told them to go and stick the floppy disk in the machine and do a software update. Well, that doesn't work anymore. We don't want to have to do that anymore. Particularly given the sheer volume of systems that are out there, we can't sort of put our employees out into the world. The wrong way to do it, illustrated by a news story from last year, is a company that makes the door handles in hotel rooms. Did a software update to all their door handles, and the contemporary verb is they bricked it. They bricked their door handles, i.e. the door handles become indistinguishable from expensive paperweight, became useless. So the wrong way to do it is to make a mistake and in some way get an update wrong, because if you get it wrong, you may end up with a product that won't do anything at all, which is kind of embarrassing, and at worst could end your business, or your reputation, or your share price, or whatever. The new way to do it, of course, is what your phone does. If you tap update on your phone, be it Android or Apple or whatever, something magic happens, and a new version of this or that app will download into your phone. There is some technical stuff going on behind the scenes there. How do you know the thing that's downloading is actually the app that was developed by the app developer and hasn't been corrupted or been tampered with in transit? Or how do you know it's the real thing? Well, what's going on here behind the scenes? So if your phone can do it, can we do it for other systems? Can we do it for defense systems? Can we do it for aeroplanes? Can we do it for, well, this so-called Internet of Things, whatever that is? Just anything, basically. Well, let's ask the internet. There's a good place to start. And it turns out there is something on the internet that tells you how to do this. It's got the imaginative and exciting title, RFC 4108. Ooh. Okay, so this is one of the so-called internet request for comment documents. 4108, it's actually quite an old document, comes from 2005. This is a document called Using Cryptographic Message Syntax to Protect Firmware Packages. What it basically is, it's a document that defines a data format and a bunch of cryptographic options for how you can package up and do certain cryptographic things to your payload to make it, in quotes, secure, so you can send it into the field. Well, that's sort of interesting. And what we were asked to do as the software team I led, we were told to basically read that and implement it. On behalf of a client, and we said, oh, okay, well, let's just do that. That'll be interesting. The basic idea, basically at the developer's end, you have something called a certificate authority. So this is a bit of software and hardware that's capable of doing certain cryptographic things. So first thing you do is you encrypt the payload. You take your blob of data, if it's code or data, I don't care. You encrypt it in some symmetric crypto system with a key that we will, for the purposes of argument, call FEK, firmware encryption key. Having done that, you then stick a hash on the end of it, because hashing seems like a good idea to ensure integrity of the payload. There are various hashed and encrypted crypto schemes. You pick the right one that you want to use. Then you add some metadata. So the metadata, sometimes called the manifest data, is stuff like, well, what is this payload? What's its identifier? What version is it? What's its date? What does it depend on? Like other components. What hardware does it run on? Is there a particular version of the hardware it needs to run on? And all sorts of other metadata you can put in there. And also things like the crypto algorithms. The metadata will say, this has been signed with this crypto algorithm, so you know which one crypto algorithm to use at the other end, and all that sort of stuff. So you add the metadata, then you generate a digital certificate, much like your web browser understands digital certificates that, claim the authenticity of certain web servers. You add a digital certificate that's based on the metadata and the hashes and so on, and then you shove the certificate on the front. You package it all up, you write it out in binary to a data file, and that's the thing you can send out into the field. Or maybe a whole set of them go as a group, because maybe you want to send, it's not just one component, you want to send a whole set out at once. So something like that happens. You can send it over any communication channel, so a carrier pigeon or email or whatever. Hopefully a totally unsecured channel. That's the idea, obviously. At the receiving end, the target platform, which is might be a laptop, might be an embedded system, an aeroplane, IoT device, whatever, receives the data. Okay, it verifies the certificate. It uses the public half of the signing key. The signing key is called an FTA. It's called a firmware trust anchor in the geeky terminology. So using the public part of the trust anchor, you verify the certificate. You verify the hashes, you decrypt the payload using this key FEK, and then you say, excellent, marvelous, and then there's something, well, you have to maybe reprogram the file system of your device or reprogram the flash memories, which is a non-trivial thing to do, or somewhere, there's some sort of mass storage, we presume, in the target system that needs to be reprogrammed, and then you hit the reset button and it reboots, and ta-da, you've got the new version of whatever it is. Isn't life wonderful? Well, can we make it simpler? If you're a UK defence company or in the UK government, you can ask the government how to do it. The government in this case actually means the National Cyber Security Centre. They're based in London and in Cheltenham. RFC 408 actually allows a lot of flexibility in things like choice of crypto systems and key lengths. The NCSC will say, if your payload is secret, thou shalt use this signing algorithm, this bulk encryption algorithm, this key length, this hash algorithm, and you are limited to exactly one suite of crypto algorithms, which is great because it means I only have to implement one suite and I don't have to implement 20 different algorithms and then the user would make some stupid choice. I'm limited to exactly one suite, and that's nice because I also have to only implement exactly that and no more. So that's fine. There is a NCSC technical standard on how to do this. If you're capable of handling protectively marked material, you can request this document and maybe you'll get a look at what it says. So easy, huh? Well, no, it's not easy. Firstly, the receiving target system might be a small embedded system. It may have very limited power. It might be running on batteries. It might not have a permanent network connection. So how do you actually get the data into it? It may have no operating system. We're talking about bare metal programming. And also this reprogramming action is happening at boot time. So it's happening because one of the things you want to be able to update is the operating system. So you have to do this pre-OS boot. So you're dealing at ring naught or bare metal programming. And that's pretty difficult. We designed this and we implemented it all from scratch. We did not just cut and paste it off Stack Overflow or use OpenSSL. No, we don't trust any of that stuff. We wrote all of this code absolutely from first principles, including things like all the elliptic curve mathematics and AES and everything. So we did it all from scratch, which was really cool to do it all because we have control. The other kicker is the atomicity of the update process. Have you got enough flash memory to withstand a power failure while you're reprogramming the flash memories without bricking the product? That's really hard to get right. Atomicity is really nasty. If reprogramming the flashes takes 5 minutes, well, what do you do if you get stuck halfway through that process? That's kind of difficult. So making it atomic and recoverable is pretty difficult. Yeah, do not brick the product is the critical correctness property. Always ensure you can at least get the product back to the kind of the factory default setting or something is quite tricky. The reprogrammer software being able to reprogram itself is also quite a laugh to arrange. On the verification front, the software was written in Spark, not Apache Spark. I'm talking about Spark, the Ada subset, because it's formal and because we can do formal verification. So we did all sorts of formal stuff. I realized, by the way, when I talk about formal verification in software, it's nothing like what our previous speaker was talking about with hardware. The hardware community used this word formal in a way which is totally unfamiliar to me. And it's really worrying that these two communities are using this term in a just weird way, different ways. Okay, when they talk about doing formal, it's not what I mean by formal verification of software. I've come to learn this. Coming to these conferences makes me go, huh? A lot, because I don't use the word in the same way. So as I said, this is all written for bare metal, so there's no operating system, there's no libraries, there's no libc under this code. There's nothing apart from our own object code. And basically on the verification front, we did a lot of stuff by static analysis. In fact, it's almost all static. And particularly, we proved it essentially crash-proof, no runtime errors, no exceptions, no buffer overflows, all done by symbolic theorem proving. This is not testing. This is totally static formal proof. Yes? Based on an assumption that the processor hardware is executing the instructions faithfully, yes. We're in a very heavily tamper-proof environment here, thankfully. We're not too worried about attackers having physical access and tampering with the hardware.
That actual hardware is, sometimes people flash something new because the hardware is not working.
Yeah. It's not a huge risk for this particular customer. And yeah, okay, there is modulo a belief that the compiler is also behaving itself and not being malicious as well. So fair enough. So we did a lot of theorem proving, and we also did things like static analysis of worst case memory usage. To give you an idea how small this gets, the object code for the core of this reprogramming infrastructure is about 5 kilobytes, and it needs about 10 kilobytes of stack. Now, some of you young people in the room probably don't remember what a kilobyte is. It's what you was lucky to have on a ZX81 in the 1980s, right? So it's small, this stuff, which is good. What else do we do? We did a lot of all the usual stuff, regression testing against the crypto algorithms, thankfully have very good specs and very well published known answer tests and reference test vectors. So we used those. We did a lot of end-to-end testing. So you take data, you encrypt it, sign it, unsign it, decrypt it. Do you get back the same data? Pretty obvious. And we did some fuzz testing against the parser. The receiving end has to be a parser for a language called the ASN1 encoding, the binary encoding format. Do you know about ASN1? It's freaky, isn't it? The ASN1 distinguished encoding rules. Pardon? Oh, it is marvelous. I love it. But it shows its pedigree, shall we say. I think it's rather wonderful. But yeah, we tried fuzz testing the ASN1 parsers, and that was interesting because it yielded no useful information at all because we couldn't crash them because we'd already proved they were crash proof. So, no, not a surprise. It was a good confirmation that the proof stuff was working as we'd expected. So we didn't really worry about things like side channels. We weren't worried about timing or differential power analysis. We didn't go for a time constant implementation of the crypto because that is really hard to do in software. So we weren't going for the really heavyweight side channel stuff, again, because the environment was largely tamper proof and not too worried about that. The bad news, you may need this. Please don't try and design how to do this yourself. It's a very bad idea. Historically, trying to make up your own crypto protocols is a bad thing. Doing this right requires a lot of care and attention. It's kind of like doing SIL4 programming or safety critical programming, but for security. Good news is we've done it, so we know it can be done. We are attempting to, the company I was involved with doing this, well, we're attempting to get the IP in this so that we could actually sell it to other companies, but that's in negotiation with the original customer at the moment. Some other issues. How the hell does the target system know the key or keys that it needs? We're into the world of key distribution and key management. That is the big elephant in the room problem. How do you get the keys that are necessary out into the world, and how do you do that? That is actually really rather problematic. What about compatibility of complicated hardware components and a complicated set of software components? That's really complicated as well. RFC 4108 says nothing about that. It just gives you some metadata that you can use. It's totally up to you to come up with a policy about what's compatible with what in terms of hardware and software. It's completely open-ended, and you have to go away and think very hard about that. And are you actually capable of running a certificate authority? It may not be your core business. Running a CA requires astronomical levels of physical security because you've got to keep the private key really secret, right? That means running, you know, hardware security modules in a tamper-proof environment, in a Faraday cage, in a bank vault, that kind of stuff. If you're not capable of running a CA, you could ask another organization to do it for you. For example, GCHQ will sign your software packages for you if you pay them a small fee. So, okay, but your turnaround time might be not be as quick as you want. So, up to you. What are we going to do next? We may well try and declassify some of this stuff so that we could sell this to people who aren't in the defense or the government industry. One of the algorithms is sensitive, so we're not allowed to talk about it. But if we take that algorithm out and plug in a different standard one, then we could make this available to anyone in the industry, which would be fine. There are some other options. Compression and differential updates is important. Updating a 10 megabyte payload is annoying, except if you could diff the old payload against the new payload and only send out the diff, then you're into this world of, and then compress it. So compressed and differential updates is a big deal that we may look at. Could we employ hardware security modules in target platforms? The answer is yes, that would be nice if they were there. So things like some microcontrollers these days do have support for hardware key storage and crypto acceleration that we could exploit. And watch out, another group have decided that RFC 4108 is actually a bit old hat. This group is led by ARM. It's called IETF Suit. It's something, I can't remember what SUIT stands for, but Google it. This is a group being led by a team at ARM who are seeking to basically replace RFC 4108 with a new structure and a new way of doing it, which will be even more flexible, particularly for low power and small kind of Internet of Things style devices. So watch out for what that group are up to. That's it. I will take questions with the insane looking tapping cat. Thank you.
Secret FPK in all the devices at the same time. And your software, so anyone who has even the basic physical access to the device will be able to use either timing or power analysis to extract the common FPK. So why do you want to encrypt the payload at all?
Good question. Firstly, there isn't exactly one FPK. There is an FEK in each device. It doesn't have to be the same FEK in each device. The FEK has an identifier which goes with the metadata, so you can have lots of them if you choose. How FEK gets there is interestingly in the standards, it just doesn't say. It just says we assume it's there. So the whole key distribution issue is not addressed by RFC 4108, and that is a colossal kind of whoa gotcha in this whole scheme. Theoretically, if each device had a private key and they were online, then you could actually do a key exchange. You could do an elliptic curve Diffie-Hellman key exchange and establish a session key. But establishing a session key requires you to actually be online with the server, which might not be appropriate for some systems. So there are other ways of doing it. But so no, it's not just one FEK. There are, but no. Yes. Yes, you need a good source of random numbers. Yeah, it's not trivial however you cut it up, this problem. So, Graham. Yeah. No, as long as you, the obvious thing to steer clear of is recursion. So the parsers were very carefully written to be non-recursive. We didn't write a generalized ASN1 parser. We wrote one that was specific for the non-terminal grammar that we were trying to parse, which is what's called the signed encrypted firmware package grammar. So we wrote a non-recursive parser. Other than that, yes, when you're coding in Spark, the code is amenable to worst case static usage analysis. If you've got the compiler support and the tools in place, it just works.
Maybe we can give only last one.
Go on.
I was interested to know your observations about the difference between hardware and software. You mentioned that there was a difference in the meaning of the word formal.
So I'll tell you what it means to me. I mean, to appeal, for example, the definition of formal in DO333, I'll look at Nick just to make sure I get it right. In DO333, which is the DO178C supplement about formal methods, it defines a formal method as a combination of a formal language and formal analyses, right? And a formal language is a language which has an unambiguous and mathematically stated semantics. A formal analysis is an analysis where the results are said to be, you have confidence that results are said to be sound, meaning zero false negatives, right? So trustworthy. Therefore, in software verification, when I talk about formal verification in software, I'm talking about a completely static and symbolic verification of correctness for all input data and all system states without testing. Okay, it is purely symbolic. But when the hardware people talk about, oh, formal, 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 and then he talks about testing and simulation, and I go, hang on. Right, so I am just confused, and you use it as a noun. You say, oh, we're doing formal. Well, I don't use it as a noun. I use it as an adjective. This is a big difference to me as well. So I'm just confused by the way the hardware people use the word formal, and I would love to be deconfused by anyone that can explain it, but probably not now. I'll move on. Okay. Yeah, let's move on. Thanks.